In this video, we will be looking at properties of nth roots. What is this up here? On page 359 in your textbook, you can look at this chart. In words, we're going to start out with looking at the product property of roots, and then we're going to look at the quotient property of roots. So, if you have here's an example. If you have the cube root of 16, and we want to simplify that, we can split this up into the cube root of 8 times the cube root of 2. And the reason I'm going to do that is because I want to simplify the cube root of 16, and in order to do that, I want to pull out any perfect cubes that are in that number, in this radicand right here. And 8 is a perfect cube, has a perfect cube root of 2. So you can take the cube root of 8, which is 2, but we can't do anything more with the cube root of 2. There's no perfect cubes that go into 2 evenly. So that would be the simplified form of the cube root of 16. So that's with numbers. If you're looking at it with variables in algebra, what you want to do is look for perfect cubes. Like for x to the 7th here, we want to figure out what perfect cube we have in x to the 7th. And so if I split that into x to the 6th times the cube root of x to the 6th times the cube root of x, let me back up here. I can rewrite this as the cube root of x to the 6th times x to the 1st, because the properties of exponents allow me to do that. And then the reason I'm going to do that is so that I can split this into the cube root of x to the 6th times the cube root of x. And I did that because the cube root of x to the 6th has a perfect cube. Remember, if we rewrite this into exponent form, it'd be we put the index in the denominator, so the x to the 6 over 3. Because 6 is evenly divisible by 3, that becomes x squared, and then we still have a radical of the cube root of x, which has no more perfect cubes in it. So this would simplify to x squared times the cube root of x. The point being, you can pull out you can split up a product. If you have the 16, so let me rewrite that. That's 16. I could rewrite as 8 times 2, and the reason again I'm picking 8 is because it has a perfect cube root. Same thing with quotients. You can split a quotient into for the square root of 25 over 16, I can split that into the square root of 25 and divide it by the square root of 16. And then you can proceed from there and actually take the square roots, and you'd end up with 5 over 4. With the same thing that holds true for this example right here. You can split up a quotient and write the nth root of a divided by the nth root of b. We're going to be using that to simplify a bunch of different expressions. So I'm just going to go through a whole bunch of examples here. Okay, first example. Pause the video and write it down, and then follow along with me when I simplify this. We're also going to be rationalizing when we do some of these examples, and this one we're going to be rationalizing when we have a denominator. So there's no denominator here, so we don't have to do that. But what I can do is use that product property and split this up into the cube root of 27 times the cube root of x to the 6th. And luckily we have two perfect cubes. The cube root of 27 is 3, because 3 cubed is 27. And then we're going to multiply that by the cube root of x to the 6th, which if I write it as an exponent is x over 3, which becomes 3x squared after simplifying. So this would be the simplified form of the original here. Okay, rationalizing. When you rationalize, generally we rationalize to get rid of a square root or a cube root or any nth root in the denominator. And this one has a square root in the denominator. To get rid of the square root in the denominator, what I'm going to do is I'm going to multiply by the square root of 2 on the top and on the bottom, because that's really multiplying by 1. When I multiply across, 1 times the square root of 2 is the square root of 2. And in the denominator, the square root of 2 times the square root of 2 can be written as the square root of 4. And the square root of 4, the square root of 4 is equal to 2. Now this is considered rationalized because we've gotten rid of the square root on the denominator. Okay, we're going to simplify and rationalize this guy right here. And the reason I wrote down these perfect cubes, 1 cube, 2 cubes, 3 cubes, because I have a cube root here. And I'm going to be looking at how I can make the cube root of 7 not have a radical with it anymore. So here's how you do it. We're going to first split it up. We're going to take the cube root of x to the 4th and the cube root of 7. And so, in the numerator, I can split that up further into the cube root of x to the 4th can be written as x to the 3rd times another x. And the reason I want to do that is because x to the 3rd has a perfect cube root in it. On the bottom, I want you to think about this for a second. If I just multiply by the cube root of 7, I'm going to end up with the cube root of 49, which is not a perfect cube. So what I want to do in the denominator is I want to multiply this by the cube root of 7 squared. The reason being is because, well, let's look at the top first. I can split the cube root of x cubed times x into the cube root of x cubed times the cube root of x. And then in the denominator, because I have 7 and 7 squared, I can rewrite that as a single, I'm using the product property but in reverse, as the cube root of 7 cubed. And if you look at this, the reason I did this is because in the bottom, if I rewrite it in exponent form, it's 7 to the 3 divided by 3, which is 7 to the 1st, which gets rid of the radical symbol. And then the numerator, I split it this way because the cube root of x cubed is in rational or exponent form is the cube or x to the 3 divided by 3, which is going to be x to the 1st. And then I have this extra cube root of x that is not going to simplify any further. There's no more perfect cubes in there. So this would simplify to x, because 3 over 3 is 1, times the cube root of x over 7. Now it might not seem like it's much simpler or that different than the original, but that original, this down here is considered simplified, and then it's rationalized because there's no more radical in the denominator. Okay, another example here. This is a little bit walking backwards a little bit, but this, if we have to take the square root of 75 and simplify it, what we're looking for is a perfect square that goes into 75. So 1 squared is 1, 2 squared is 2. I'm sorry, no, it's not. It's 4. 3 squared is 9. So these are my perfect squares over here. I'm looking for a number, the biggest number that goes from this list that goes into 75. And I'm going to keep going here because none of these go in so far. This is 16. 5 squared is 25. 25 does go evenly into 75. And if you look at like 6 squared, it's 36. That doesn't go in. 7 squared is 49. 8 squared is 64. I'm getting too big. This number obviously isn't going to go, you can't multiply 64 by anything to get 75. So this is what we're looking at right here. That is a perfect square. 25 is a perfect square that goes into 75. So I'm going to split 75 into 25 times 3. And then you can use that product property and split that up into the square root of 25 times the square root of 3. And then we can take the square root of 25, which is 5, and then we just leave the square root of 3 because it doesn't have any more perfect squares that go into 3. Okay, another example. Why don't you write this one down and try to do this on your own, and then come back and check it. So we have the cube root of 125 and the cube root of x to the 6th. And if you look at your list of perfect cubes, the cube root of 125 is 5, and the cube root of x to the 6th, rewrite that as an exponent. 6 divided by 3, remember this index goes in the denominator. And you end up with 5x squared, which does look more simplified, but that's what you're going to do. You're going to, and that's only because 125 was a perfect cube, and so was x to the 6th. Okay, go ahead and try to rationalize this problem, and then come back and check it. We want to get rid of the radical symbol in the bottom, and so the 3 has no perfect fourth roots in it. So what we need to multiply by is something that will allow us to pull out a perfect fourth root. So if I multiply the fourth root of 3 to the third, watch what happens here. The top is 3 to the third is 27. So I can write the fourth root of 27, and then on the bottom I'm going to end up with the fourth root of 3 times 3 cubed, which is 3 to the fourth, and hopefully you're starting to see that that's actually going to be 3 to the 4 over 4, which is going to be just 3. So I have a fourth root of 27, and then the denominator I have 3 to the 4 over 4, writing it as an exponent instead of a radical, and we end up with fourth root of 27 over 3, and that is simplified. And if you aren't sure about if this is simplified or not, we're looking for 1 to the 4th is 1, 2 to the 4th is 16, 3 to the 4th is 81, way too big. So there aren't any perfect fourth roots to go into 27, so we're done with that. Okay, one more example here. Square root on the top, I'm going to split this up. Square root of, and I'm going to write x squared times the square root of x, because I can take the square root of x squared, and then I have a leftover x underneath the square root. Move this out of the way, and then I have y to the 5th, and if I'm looking at a perfect square that goes into y to the 5th, it would be, we'd have the square root of y to the 4th. Basically what you're looking for is whatever the index is, this exponent has to be perfectly divisible by that index, and the index here is 2. Recall that if there's nothing written there, it's a 2. And then we have z to the 4th, which is a perfect fourth root. In the bottom, I need to rationalize that. I have a cube root of 5, so now I want to multiply the top and bottom by the cube root of 5 squared. All right, so then continuing on here, I have the square root of 25, which is 5, the square root of x squared, which is x. I have a square root of x still that can't be simplified any further. I have the square root of y to the 4th, which is y to the 4 over 2, which is y squared, which you can just write that. And then the same thing with the z to the 4 over 2. In the denominator, when I multiply the cube root of 5 times the cube root of 5 squared, I get the cube root of 5 cubed. Oops, I had to do that on the top as well. I can't just multiply on something on the bottom, I have to also multiply the same thing on the top. So I still have this cube root of 25, which is what 5 squared is, up there. And then simplifying further, I end up with, I'm going to put all the stuff that is in a radical at the end, and I'm going to put everything else at the beginning. So I have this 5 and this x, and this y squared, z squared, and then I have the square root of x and the cubed root of 25, all divided by 5. And looking at this, I can still simplify by eliminating the 5. So you end up with x, y squared, z squared, times the square root of x, times the cube root of 25. All right, and that's that. So you guys try to do some practice. Before you do that, I want you guys to look at page 360 and study the properties of exponents, if you need to have a refresher on that. And we're going to work on 5.5 through 5.6 practice. All right.